Hey, welcome back to yet another video. Today we'll be looking at Protocol Covert Channel, a method where attackers hide information within legitimate network traffic such as TCP, UDP, or HTTP to bypass security policies. And specifically today we'll be looking at this challenge, Sniff. Description: we received a pickup file capture from a corporate network device after suspected incident. Help us investigate what happened. So this one is a network.pickup. So this is a network capture file. We are going to analyze it using two specific tools. One will be tshark, the other one will be Wireshark. So you'll open your terminal and access where you've downloaded it. So I've created this directory called Protocol Covert Channel. So we'll use Wireshark and then specify the capture file, then press enter. It will start up Wireshark. Mine is already open. So okay, yes, so here's the file, network.pickup. Once you get a file like this, first thing you need to do is just go to statistics and then conversations, and then since most of these IP addresses are IPv4, you can just select here IPv4. So we are in Wireshark conversations. So we are sorting the packets. We have seen that 192.168.1.69 and address 10.10.10.10 have exchanged 3,814 packets. So this is interesting, and we look at these IPs. We'll use them as a filter to look and see what were they talking or communicating inside the network. So 192.160. So you come here in the sort in the filter and just apply IP address equals. You can choose to use EQ or just double equals, but for me we use this one, IP, and then the IP address 192.168.1.69 and 192.10.10.10.10, and remember to always IP address equals. So look at the conversation. So interesting, there is both TCP connection requests and then HTTP network. So we can see the TCP protocol and HTTP and their conversation, and something interesting. Let's try and follow one HTTP request. So follow HTTP stream. I look at it. So this is a post of version HTTP 1.0. The user agent, and then the user ID. This looks like session details for a specific user, because you can see this, it has the device ID, the user ID, and then the session ID. Okay, so yes, let's look at another one. Okay, to make it better, let's just do this. We'll do the same search. IP address is equals 192.168.1.69 and IP address equals 10.10.10.10 and has HTTP request. Let's just see all the HTTP requests that these two sent each other, and we can look at this. We can expand these. These are the frame number, the time, the source, and the destination. So we can already see something interesting, the way these requests are changing. These posts 192.168.1.69 sends a post request with HTTP version 1.0, application JSON 192.168, and also look at the time difference. This is just a small within a small time, so this can't be. Also, this also helps you identify if it is automated behavior or it's human behavior. And we can look, and also something else you can look at is 192.168.1.69 sent delete request to star CSS, and then HTTP version 1.1. Now check this is the interesting part. You see how this HTTP version 1.0 is changing, and then it comes and the next request is version 1.1. What is being used to exfiltrate the data is this last part, HTTP version 1.0. See the 0 part, that stands for 0 in binary. Now if this was the attacker was trying to exfiltrate some data, just convert it into binary, and then the first bit of it is a 0, and then you see the next one is a 1, and then we see let's just, but first we need to confirm our suspicion. But for me, we know that this is an example of a protocol covert channel attack, and attackers do leverage this to exfiltrate data, and this, as you can see, it is appearing as normal traffic. So we've seen that there's something weird about the version, and it's changing. The way it's changing, it's not normal. This is not normal user interaction with the website. This is how attackers automate these requests in order to exfiltrate data in and out of the network by just using this final part. See under the HTTP version 1.1 how the 0 in 1.0 and the 1 in 1.1 are changing, is being used to represent binary data, because as you can see, this is 0 1 0 1 0 1 1, which as you know, the zeros and 1, this is how computers communicate. This is binary. So just for us to confirm, we'll use tshark, and then tshark network.pickup, and then use y. For our filter, we'll be using http.requests, then -t fields will be specifically looking at the http.requests.version. So we'll just let's look at it, and you can see have these long list, and look at these 0 1 0 1 0 0 1 1. Even if it's just exfiltrating this small part, I think this is some information. This can be decoded into information. So let's just strip all these. We need to look at this binary that is being represented by these many HTTP version types. So to do this, we'll be using sed. I don't know, I call it sed, and then okay, let me just write it up first clear the screen. So we'll redo the command tshark, and then r for to read network.pickup, and then /y for hyphen y for http.request. okay, I just press tab, request, then -t fields -e, then -e is this means that we are filtering for HTTP request, and we want to specifically to see the HTTP version. That's the field we want to see, and we get these. So after getting these, what do we do? What we need to do is to remove all these parts and just be left with this final bit, so that to see if these actually decodes into some binary, we need to strip this command and just remain with the final parts. So that you can just remain with the bit part and you get something like this. As you can see, this is a stream of 0 and 1. So let's store this in a binary. We can store this as a string, and then let's try and convert it back into text and see what it decodes as. So the next step will be just to quit the program, the command, but now we will output it. You can output it to something like binary output.txt. I already did, but now you can do the same, binary output.txt, and then get something like this. Then we'll open it with VS Code. So you can just ls to confirm just it's here. Then we now decrypt the flag using Visual Studio Code and Python. So this is it. This is the script. This is what the script does. First, you open binary.output, so you can see a stream of bits got copied. Now we're going to use this Python code to extract the binary string, and then what we'll do, we're going to replace the new line, and then we'll decrypt the flag. Let's redo it so that you can understand what the Python code does. So first things first, we will start with reading the binary string from binary output. So we'll say binary string is equals to open. We need to open binary output.txt, read, then this. So this we just say we read it as a string, and then we can print it out. Say binary string, and then you can choose to run. So we just get this as being displayed by tshark. So next thing, we need to remove the new lines. Let's remove the new line so that it can just be one long stream of data. So what we need to do, we can choose to comment these, and then what we'll do is binary string is equals binary string dot replace. We need to replace the new line with an empty. Yes, we replace the new line, something empty. Now we can print the binary string. Let's see how it looks like. Yes, something like this. So with this, now we can work around this and now group them into bytes. Bytes is 8 bits, so 1 2 3 4 5 up to 8, and then decode the bytes into decimals, and then from decimal we convert it now to ASCII characters to see what letters they actually represent. So you can see this is the binary string, but this is a very long one. You need to group them and get bytes, individual bytes from each one of the groups. So what we need to do, we'll use the modulus. What we'll do this for I in range 0 to the length of binary string. So individual character string What does it do? We'll need to check if it's a full byte, full 8 bits. So I modulus 8. So if it's a full byte of 8, it means that there will be no remainder. So this function only is only used to confirm that this is now another full byte. Now we can represent it. So what we need to do is byte is equals to binary string. We need to sweep the binary string up to, so it's I up to, from I up to I plus 8. Yes, byte. And then let's print it out and see how, for instance, how the byte will be grouped. Grouped. Okay, just save it and then python extract.py. You see, now this is being grouped into individual bytes, and these we can use to convert back to decimal. Since this is a full byte, it represents data. This is how computers represent information. And since you have all these bytes, we can now convert them to decimal, and then from decimal to the ASCII characters. So since we have byte, now we can convert it to decimal. To convert it to decimal, you can say let's say decimal small value, okay, is equals to just int, and then you say byte, the byte string, the byte, and then so as you remember how to convert from a decimal value to from binary to decimal, you divide by 2. So this is just what exactly is happening. So then let's first print the decimal value, and then you'll see. So we'll comment this one, then yes. So this is now the decimal equivalent of the binary bytes. So what we need to do now is just to see the ASCII characters themselves. So from this decimal value, what we can now take this decimal and feed them into ASCII to know what these values represent. You know, each of these values represent an ASCII character. So let's look at it. Print decimal value, just comment it out. So what we'll do, we can say we can come up here and say the flag is equals to an empty string. And then from there, what we'll do, we'll say flag plus equals for each byte, flag plus equals. So to for you to be able to see the ASCII value, you just use this chr or char short form, then call the value, should be a number. So this, so flag plus equals decimal value, and then after this iteration, what we'll do, we'll come here and print the flag. Then plus flag, and then save it, run it. So as you can see, we have successfully decrypted the flag ASCII sat hidden in plain text inflow. So okay, don't know, something like that. So but we've gotten the flag. Yep, and that is how Protocol Covert Channel is done. So you already solved this, so you have completed the challenge. Thanks for watching. Yeah, and that was our video about Protocol Covert Channel. Stay tuned for more. Happy hacking.